Okay, what we already see the characterization. For example, if you send the single photons to do some beam splitter, 50-50 probabilistic beam splitter, and if what happens if we try to divide them, and how what is the behavior of this experiment? What do we observe? And for indistinguishable single photons, how do they behave at this beam splitter? We already saw the results, but on an integrated perspective, now it's time to measure this behavior from integrated circuits. Now, what we have is a usually in an optical setup. It's just a regular optical setup, schematics of optical setup. What we have usually a tunable laser or broadband light source. It depends on your application, and we send it to a polarization controller. And if you remember, on the integrated circuit, we have only some available modes, for example, polarization or spatial modes to deliver this laser, and they work only these modes if they overlap of the signal and either photons. And this is our, for example, four-way mixing or SPDC ring resonator here, chip here, placed on some motorized stage. And we have some optical components to focus the laser beam onto this chip, and then collect them and send to some optical spectrum analyzer or spectrometer to get this transmission behavior from this chip and correlate it with the laser if they are already good agreement, if it's the expected result. Then what we can do, we can just put a flip mirror here, and if we don't want to measure the spectral measurements, we can just filter out the laser again and send a beam splitter, for example. If we observe it, for example, from the one of the if we separate the signal and idler photons from with this beam splitter, for example, let's say this is a polarizing beam splitter and it's a type 2 process from SPDC, it will produce horizontal and vertical polarization states. So let's say horizontal goes this way and vertical goes this way. What we will observe, this is the G2 function, which is the intensity correlation function from this experiment, and it has a very high, like it's normalized to some higher order modes. And I am sorry, this axis is not seen here, but it's the time difference between the detection event. Okay, consequent or the large time difference from this detection event, what we see a large G2 function, which means this is a bunching, strongly bunching behavior, which we cannot observe in nature. Then it suggests it's a time correlated. It might be a pulse signal too. We don't know about the quantum mechanics now, but it's a correlated, time correlated source now. Okay. What we do in a tabletop experiment, we see the tunable laser, for example, here. It's from an old setup. It's a tunable laser with a kilohertz narrow bandwidth. Why? Because if you have a very like a cavity with a high quality factor, then your full width maximums will be very narrow. So you want to scan this. You want to scan this transmission spectra with very narrow laser to see this behavior or this transmission drop, because these modes belongs to the cavity. So you want to excite, for example, from this mode and generate signal photon pairs from this one and this one. Okay, then this is the optical spectrum analyzer. It's basically it can be monochromator, etc. Gives you your what it gives you is the spectral behavior of your source or laser, etc. This is the polarization paths to correctly manipulate your polarization states in your optical fiber, which is different from the free space propagating waves. So then you have some lensed fiber here, and you can see here this is a usual optical fiber with a lens tip on that. Why we need this type of structure? Because we can reduce the mode diameter coming from the fiber to very small sizes, so we can integrate to the chip. as you know, if we use, for example, here, try to couple the laser to the waveguide directly, the dimension of this waveguide usually very, very narrow. For example, 500 nanometers. Well, as you can see, due to the ray conditions, you cannot reduce your size unless you are using very high numerical aperture lenses or very short wavelength lasers. So what you do, you will also need to implement some fiber coupling of nanophotonic structure here. I'm not going to get in detail here, but from the previous talk, there was some grating couplers, which is the most popular today. Okay, then you want to get an observation how is the light is scattering through your chip. So there will be some chip is located here, but it's not seen here. You will need to use some microscope setup to check the light how the propagates here, but it's just a usual microscope. Then you collect here, and these are the single photon detectors, and these are the motion control electronics. So let's check the spectral measurements. Like I said, you did the spectral measurements. You see some large detuning or large range spectral measurement, and you saw the peaks. This and separation from the peaks is like 0.1 nanometer. Okay, this which is called free spectral range. You can also get this result from the numerical simulations I already mentioned yesterday. The same. And you can just fit this function around this one of them. You can get the full without maximum. It depends on, like in material science, depends on your material or the equipment. But if it's narrow, it's usually Lorentzian. Okay. Then you get this the fit function. Then you observe that, and from this value you can calculate, for example, Q factor. So if you can phase match this structure according to formula I showed you yesterday, you can produce approximately 10 to the 18 pairs per second if you don't have any losses. But for nanophotonic in real life, losses are very impactful. You will probably end up with a few thousand. Okay, unfortunately. But this is another topic of the engineering, nanophotonic engineering. So this is the SEM picture of this structure, and as a side note, from a material scientist perspective, hardest thing to do is this gap. You need a perfect gap and perfect interaction between the waveguide and the ring resonator for evanescent coupling. So the etching and deposition and lithography has to be perfect, which requires tens of years experience. What we do next, we will separate the signal and idler, okay, in a different paths. Then we will use narrow line width filters to check this correlation, this G2 peaks, if it stays there. Okay, this is for example, then the intensity here is this G2 function intensity, all right? If we see this kind of behavior, if we see, for example, it's a diagonal shape, you can easily say that this is a perfect correlated photons, which you cannot use for single photons as a single photon source from this. You need to change this behavior. But another side, you can easily generate, for example, with an extra little bit setup to create entangled photon pairs, polarization entangled photon pairs from this single photons. But in the end, what we want to observe, very small spot with in a wavelength from both direction, like a very small intensity spot, and then you can have the perfect decorrelated photon pairs, which we require, right? We want a single photon state from different sources that can be, and these are indistinguishable between different sources, so we can apply gate operations or measurement operations on them. Second part, if it doesn't work, we don't need this for heralded single photon sources, but if you have a deterministic single photon source, like defect centers, quantum dots, like I mentioned in the Monday, and then you need the electronic state lifetime. Why? Because like I said, since they are embedded in a solid state environment, it will interact with its bands, or you can call it's the environment. And it might be electron-phonon interaction, dipole-dipole interaction, other electric fields, etc. And both of them broadens your spectral line shape, or like I said, make them decoherent. So if they are decoherent, then they won't be indistinguishable to each other, even from the same source obtained from the different time zones, times. Okay, so you get this, you measure this behavior by applying a pulse laser. Then you stop for a limited time, and you see this spontaneous emission from this two-level source. Then you will see some exponential decay. Then you can easily, this is an intensity change, and you can, as you can see, it's already exponential decay, and you can either fit with 1 or 2 or 3 states, depending your how many interactions in there, if it's 2-level or 3-level states. Then you can check if it's a perfectly emission, if there is no pure dephasing like electron-phonon interactions, etc., then you will see this T2 values will be equal to the 2 times T1, which is you are measuring now T1. What we call that, if you measure that, if you obtain that, what we call the Fourier transform limited lifetime. Then you can easily implement for a photonic quantum computer with the high fidelity gate operations. Okay, now move forward. Now the temporal characterization. I call it all of them temporal. There are a lot of them, depends on your single photon or photon pair sources, but you need to do that before you apply a photonic quantum computing. For example, let's start with a simple single deterministic single photon state, which emits a single photon every time you apply a pulse to it. Okay, and you collect them efficiently. So this, you send this single photon, for example, 50% reflection and 50% transmission rate beam splitter, just a regular beam splitter, probabilistic beam splitter. You see that either of the photons goes to the detector 2 or 1. It cannot go that both way. You might, in the experiment, sometimes you do. Why? Because there depends on your lightening of your room. Depends on how the stray electrons in your room, and there is the cosmic radiation affecting to your detector also. All right, so there will be always some unwanted correlations. So they, like I said, from an experimental view, for a single photon Henry Bromtooth experiment, you never reach the zero. It's impossible. You can get very close, like 0.0000 loss of zero, but never absolute zero. It's impossible. Now, then about these arrival times, let's say this is the time the detection events you get from these detectors, and like I mentioned before, you are connecting this detector to some cross correlation device, or what we call time tag device, etc. What generates when it detects these detectors detects a photon, it generates a 1 or 0. Let's say this. Let's keep it simple now. And this is the detector 1, channel 1 on top, and channel 1, channel 2 on bottom. And as you can see, it's a little bit shifted to each other. Okay, like say I can this is this increasing value is time. It's time beam. For example, I measure this detection event every 5 nanosecond. Okay, in first nanosecond, I saw, if you check the first value of these vectors, I see 1 in both neighbors, which should be possible. Okay, but I check the second nearest neighbor, delta t equals to 5 nanoseconds now. And this is the rectangular area. What I see, there is 1 in the channel 1, and there is none in the channel 2. Okay, and then I check this second second order relations, like this one, the other ones. Then I increase the delta t, scanning all the range. I will give you some experimental data. It's already should be on the cloud. And you can just produce your own algorithm to calculate this G2 function. Okay, So in experiment, this is what you observe like this, but this is from continuous wave laser source. If you pump it with a continuous wave. With a pump laser, it will be a little bit different, but you can already see similar effect. But this is for, like I said, top port for a deterministic single photon source. So for a probabilistic single photon source, in the first talk, I already mentioned to you and gave you a simple homework. What you observe if you just independently, for example, check the G2 function or Hanbury-Brown twist effect, if it's there from a single channel signal or idler by itself without checking the other photon, what you will see is a thermal photon behavior. It's not single photon behavior. So you need to check them simultaneously to calculate. For example, to see this anti-bunching effect, you need to, for example, get the photon detection events as a trigger or the gate effect from the signal and check the correlation single photon Henry-Brown twist effect with this idler information. Then you can see this. Otherwise, you cannot observe this effect. It's these photons always heralded together or created together, and there are already other processes to to calculate G2 function from this in the previous slide here. What we only calculate the two channel correlations, which is easy. But for this, we need third order correlations. It's not third order correlation, let me correct that. Correlations between the three channel, which is a little bit hard, but it's possible. Okay, and like I say, for a deterministic source, this the delta t, you plot it and you see it never reaches the zero, but which value is good? How do we determine it? I mean, if it's 0.8 is good, if 0.1 is good for deterministic single photons, which value is good? Where in principle, for an experiment, you need to normalize it, right? You need to, what do you measure? You measure the intensity, which is in arbitrary values. So you need to normalize this G2 function in the long range interaction. Because like I cannot show the whole picture here, there might be some other defects around creating bunching around the anti-bunching behavior. So you need to normalize this behavior on the long time scale. Then you, for example, say that value is a 1. Then you need to check compared to this one, how deep is, where is the deep? 0.2, for example. If it's below 0.5, you can safely call that this is a single photon source. But the visibility of this G2 is not that good, okay? Sometimes it's good, sometimes it's bad. You need to improve that. For example, what you can do, you can use narrower bandpass filters, polarization filters, couple it a single mode fiber to clear all the other special modes from your system. And for a probabilistic system, and there is, we can define as a purity. It's very similar to the joint spectral intensity or GCI measurement. You just check the one channel and G2 two photon correlations, intensity G2 function or intensity correlation from this function. What you actually get from this probabilistic photon source, you get this multi-photon or multi-mode behavior usually, and what we call this mode Schmidt modes. So when you observe this, like I said, you see some, instead of this behavior, you don't see anti-bunching behavior, but bunching behavior. Okay, but this is quite useful again. If it's well, the value usually is between the 2 and 1. You cannot go below 1, like I said. But if it's close to the 2 or very close to the 2, it's your single photon state is very pure, not correlated with the other photon pair. Then you can say that you might be able to use it as a single photon source for a photonic quantum computer. But if it's close to the 1, then it's maximal length. You can easily generate maximal length photon pair. And if you see, what happens if you see larger than 2? If it's possible. Well, it's quite possible, and it's another homework. I want you to check a little bit about it, okay? And this all the measurements here, unfortunately, affected by the background noise. So, like I said, you need to cover your setup, maybe RF shields, optical shields, narrow band filters. Carefully protect your optical setup from the background. And the second parameter to efficiently determine how good is my heralding single photon source for photonic quantum applications is the heralding efficiency, which means you just measure the photon detection events consequently or in same time in either and signal channels from this photon pair source, and the rate of detected coincidence in a time window, like for example, let's say this is a heralding single photon source value. If you see ones always together, that's a good source, which will give you a very photon coincidence detection rate. RSI will be very high here compared to the single detection events. Okay, this is a normalization and will give you the Kioshko efficiency. Then you get to the brightness part. Well, brightness is not a easily defined parameter, but in the literature, what we define is you measure your heralding efficiency, then you normalize it with the anti-bunching behavior, because in the if you don't measure them in a 3D detected environment, you might see this multi-photon pair events generation, because SPDC or this three-way mixing process in SPDC doesn't create only photon pairs, also multi-pairs simultaneously. And if you increase your for example, pump laser power, the probability of this increase exponentially, unfortunately. So you need to stay in low power. Even these powers, you can also already create them. And these single photon detectors, they are not photon number resolving detectors. Like I mentioned, I think it was the second day, Tuesday, there are some quasi-photon number detectors approach in the literature, but they are not commercially available yet. So you only detect if there is a single or more photons altogether. It's just the limit of the detection, not the photon number. Okay, then you normalize this or correct this your observation. Then you add some heralding efficiency, your pump power, and your fiber coupling efficiency, and you get the brightness from this value. And second important one is the coincidence to excitation ratio for heralding single photon source. Well, like I said, there are the multiple photon pairs, and uncorrelated events might be detected simultaneously. Why? Because there are dark noise, electronic noise, dark background, multi-photon pair detection can happen in your coincidence window simultaneously. So how do you get rid of that? Well, you can easily, if you make a two photon detection event simultaneously in both channels, and you just check the second order intensity correlation from this measurement, you measure this value, which is CAR. And there is some mathematical algebra. I won't go into too much detail, but the slide has the correct information. This is the literature is here. So what you see, you just make a subtraction from the maximum value and you get a CAR value. This CAR value is quite important. If it's good, if it's high, and then it's a very good source, can create photon pairs efficiently instead of multi-photon pairs, etc. So you want to measure indistinguishability from a single photon source. It doesn't matter it's or heralded or what. Like I said, if it's heralded photon source, you need to detect the heralded photon source simultaneously. So what you need to do first, like I said, you need to check this for both photon sources. For example, if it's heralded single photon source, you need to check this behavior from the joint spectral intensity measurements. If it is like dot-like structure, it's not like a diagonal shape. All right, this is mostly important. Then you can just apply. You can just send your signal photons to direct the detector to check the heralding effect together. For example, since a probabilistic source, this photon phase might be produced, but this might not be produced in the simultaneously. So you need to check this correlations between these detectors. When you detect the photons simultaneously, then this gate can operate. So it's like post processes gate. Okay. And then you check the correlation from the idlers from this individual single heralded single photon sources. And this is just beam splitter, and there is a phase shifter, which we change the phase of this phase shifter in an integrated circuit, like I said, like either polarization, thermal, or other methods. Or you can just change the coupling coefficients, the directional coupling. Okay, it's possible. Then what you see from the fourfold coincident events, this Hongo-Mandel behavior, if you are lucky. Then from this maximum and minimum values of this coincidence, you can calculate the visibility of system. And if it's very close to, if it's very high, then you can use this single photon source simultaneously on different sequential gates. But the problem is here with the heralded single photons, if you detect the signal photons already here, goodbye. Your gate is one time only. So this is another problem of these gates. So let's, before do that, let's, let me show you some basic GU2 photon correlation data. Okay, I don't know if you can, I can zoom in. So when you make a measurement, these time takers usually what they do, they assign an integer like with the corresponding to this resolution. For example, let's say this time taker device creates time takers when they detect a photon with the 1 picosecond increments. So this is like this large picosecond, but the internal clock of the system always going to the infinity or resetting at some point. So it will be large numbers. So what you do, you also get this channel information here. So for example, you can just check, for example, very close delta T. You can check just the if there you can how can I put it? You can just check the correlation between them. Let me show you a little bit sample here. This is a previous code, but it's quite similar indeed, and you can find it in the literature. You need to load this file to MATLAB code. Then you can just, what's the maximum distance delta T you want to calculate, all right? You cannot calculate the infinity, so you need to put a boundary to delta T, okay? Then what is your beam size, like what is the minimum correlation delta T, okay? Or your delta T incremental values. Then what you do, you subtract these channels. For example, you have two vectors, you subtract them to this direction, and you keep one of them constant. It's a simple algorithm. Well, there is equivalent of them in the classical electronic engineering literature. It's a cross correlation, but it's a little bit different. So when you run this code, anyway, yeah, I don't know. I need to debug now, but it's not the time. It was working yesterday. Anyway, you need to calculate. You get this function from this value, but for a pulse signal. Okay, it's already in the cloud. You can just write a simple script. It's a good good approach to learn how these time correlations, how this equipment works. You get the raw data from them. Okay. Now let's move to the continuous variable system measurements. I already mentioned a few times already, but in the end, there are already available integrated continuous variable sources. Like I said, you can use SPDC or spontaneous four-way mixing to generate squeeze states. You just need to put in a cavity and apply a very bright pump signal, or use a cavity to increase the interaction time. Okay, but now you don't measure the Fock states or number state. What you measure RF response of your detectors, but these are regular detectors, and you don't measure this RF response by itself, but you just subtract their current. You plug in down the RF spectrum analyzer, which is like you can think as a complicated oscilloscope, but it can give you frequency resolution, or it can separate different signals from them. And for example, from this source, we see the modes created or can be used from these oscillators. Here in the squeeze output, we see only some of them are created, because the laser are filtered out and cannot be used for system. So if we check the RF response, for example, this is the shot noise. Shot noise is the absolute minimum of electrical system can reach it. For example, you are using an FTIR spectroscopy, etc., like LIGO. You can reduce it by increasing the photon number, but to limit, because the photon number is limited. But after that, you cannot go below. But using the squeezing, and if you check this by RF response with a periodic time interval, you see it goes down and goes up like a periodic measurement. Then what you observe, this squeezing in half of the time interval, you see the squeezing, then anti-squeezing, squeezing, anti-squeezing. You decreasing the uncertainty, then adding the uncertainty together, and the total is obeys the uncertainty principle. You are not breaking it. But in the equipment, you see that. And for example, these are two different equipment, right? If you observe this behavior, you can easily call that these are. You need to do a little bit mathematical calculation, but you can call this EPR state. Okay. So in the end, what we need to consider, we need to minimize the losses. And since we are working on very, very low powers for a single photon level, etc., and material science related or the deposition or E-beam related losses are very impactful on system, we need to reduce the input and output coupling losses. Then we need to maximize our fiber coupling efficiency to the system both way. And then spectral measurements, you can do the spectral measurements just like easily with multimode fibers or multimode free space applications. But to observe the pure single state correlations, like it's in the already range, you need to use single mode fibers, okay? Or polarization maintaining single mode fibers, depends on your application. And unfortunately, fortunately, photonic quantum computing, gate-based or mission-based in this area, I don't know for the future, requires indistinguishable single photon sources for gate or measurement operations. Then you need to observe Congo model between different single photon sources. Now, I will stop here. Why? When you reach this technology level, then you need to find an algorithm to use it. Without it, it's a like sophisticated machine. It can do something like that, very nice. Like QX company based on the Netherlands, like already mentioned, they just shown this. They said, okay, we have a nice calculation machine, quantum computation machine. We don't use any for like Gaussian boson sampling, etc. But they stop there. But usually you stop here. But if you have a good algorithm like boson sampling, discrete variable, continuous variable, doesn't matter. You can just continue and maximize the priority, minimize the correlations, etc. And in the end, you get the ideal single photon source, and you can make the calculation on this integrated platform. And that's all for me. Thank you. And if you have any questions as a follow-up later, you can always write an email. Yeah.